Welcome to this video. This is a demo for 142 Computer Organization at the University of Pittsburgh. In this video, a virtual machine is designed to implement this particular instruction set architecture. 3 different types of instructions are supported here. The register block, the instruction memory block, and the data memory block, together with the program counter and the memory access register, are critical in the implementation of this instruction set. In a real implementation, the size of the memory blocks have been reduced to 64 words each. Although the instruction set is quite simple, I still had to design a data path that is capable of supporting a variety of addressing modes. Each of the 8 individual instructions requires a different data path, and to reduce the number of hardware we need for this data path, we must make each instruction to share the same hardware as much as possible. Next, I will go over how each instruction is implemented by the data path. In this schematics, as you can see, a pipeline data path is used instead of a single cycle one. This particular data path is similar to a standard MIPS processor in that it has the instruction fetch stage, the decoding stage, the execution stage, the memory access stage, and the write-back stage. Every single instruction must be fetched and decoded, while some of the instructions need the ALU and some other instructions need to access the memory. The write-back stage is necessary for any instruction that needs to update the content of the register. The hardware control unit contains an instruction buffer, which is used to generate stall signals whenever there is a branch instruction or any other type of data dependencies. Because all memory access instructions do not require the ALU, the memory access register is moved into the same stage as the data memory block. Let's look at the instruction that is used to update the content of the memory access register. Let's take a look at the control signals to see how this particular instruction is handled by the processor. The LA instruction does not update the register, and the ALU performs an add function. Let's follow it in the data path. First, the instruction LA is fetched. In the next stage, it is decoded, and the register LA is sent into the ALU, while the immediate field is side-extended and sent into the other input terminal of the ALU. After the addition, the result is used to update the content of MAR, and no write-back is necessary. Let's take a look at the memory access instructions next. We will see that they in fact do not depend on the LA instruction. Once the memory access instructions are fetched, they are again sent into the decoder, which grabs the LA register and sends it into the ALU, which in this particular case does not do anything to register LA. Depending on whether the instruction is memory read or memory write, the content of register LA is either stored in memory or updated by the data stored at the location of MAR. If you are writing to memory, the location of MAR is also the one you write to. The R-type instructions are also very straightforward. After the instruction fetch stage, the R-type instructions are decoded and its 2 input registers are sent into the ALU, which performs the appropriate operation based on the control signals decoded in the previous stage. Also, all R-type instructions will write to the first input register. And because the register content is not updated until the 5th cycle, the next instruction, if it depends on the previous one, must be stalled for 2 cycles. The branch instruction, however, will stall automatically because the next instruction fetch will depend on the result of the branch instruction, which is completed during the execution stage. The execution stage generates the control signals that multiplexes on 2 different PC addresses that will be fetched during the next cycle. The jump instruction is just like the branch instruction, except that it does not depend on the content of RA. It will always take the branch, represented by the address field of the instruction. Knowing the data path and the truth table for control signals, a simulation program is written to implement this processor. In order to show that the pipeline processor is doing everything it should, a test program is written in terms of the instructions offered by the instruction set architecture and then translated into binary code. This test program is the standard algorithm of finding the greatest common divisor of 2 integers. The input integers will be loaded into register T1 and T2, whereas T3 and T4 are temporary registers required to make register transfers possible. Because register transfers are necessary when some variables must be copied before its values are modified. In this particular case, it is very likely that using memory would be easier than using a temporary register. However, if this pipeline processor is behaving properly, then no matter how an algorithm in higher level language is compiled, the result should always be the same. I will take the binary code and load it directly to the instruction memory by using a function named installProgramA, which acts like an input device that modifies memory directly. This instruction file contains the number of instructions to be loaded into instruction memory, and every other instruction is shown in binary code. The first instruction will be placed at address 0 in instruction memory, which is also where the program counter starts. Functions like showMemory and showRegister will act like output interface. Now, I will compile and run the program. Notice that the input integers are 7 and 3, which are loaded into register 1 and 2. Since they are relatively prime to each other, the result will be 1, and it will be written into the first word in data memory. For now, I will show you the operation of the pipeline processor cycle by cycle. Oh, wait. I don't think I'm displaying the instruction buffer, so I will go back to the code and change it really quick, so that I will be able to explain which instructions are being processed and what is happening at every stage. Okay, I'm just going to exit and go find where instruction buffer is displayed. I don't think it's in instruction decode. It's probably main. Main. Let me find main. Sorry about that. It already took me 3 hours to make this video. And I would never be able to make a living by running a YouTube channel. Okay, here we go. Instruction 1 is going to be the most recently fetched instruction. Instruction 2 is the next most recent, and so on. Look at the content of the instruction buffer. 2 R-type instructions with the same RA fields are right next to each other. That is why the pipeline is old. Let me finish the first instruction really quick. Because the second instruction cannot be decoded unless the first one is written back. This is precisely what's happening here. Write back of the first one, decode of the second one, and the fetch of the third one all happened at the same time. God, this microphone is terrible. Anyway, we can see that the first instruction is finished after 5 cycles, which is what we would predict based on the pipeline processor system. Now, I will let the simulator run by itself without me stopping it at every cycle. Since this program only has about 64 bytes, I will let the program counter run to 70 to guarantee that this program is finished. The result again will be written to the first word in data memory, which should be 1 in this case, because the input integers are relatively prime. I will also get rid of some of the displays, because we are only interested in the final result right now. The video is going to look a little bit weird, because the video capture software can only capture so many frames per second, while the simulator is running really fast, relatively speaking. I will compile it and here we go. You can see that the result 1 is written to the first word, or the second byte because of small endian convention. Let's try some other numbers. How about 178? Wait, I have to encode it to binary. I just use 65 because it is easier. And for the second input, I'm going to use, let me see, yeah, 26. So the result should be 13. And I will compile and run it. Might take a while. After all, this program has 32 instructions. Each would take multiple cycles, and the program itself has loops. Wait, it's finished. You can see that 13 is a result written back to the first word in D memory. Some of the side effect is that I will also need to use other registers. Let me try something else. I don't really know what the result is going to be. Again, I'm so sorry I can't show it to you in person. It's really hard to go over code in a video. Besides, I make terrible videos anyway. Oh look, it's 4. Let me see if it makes sense. Yeah, it works. Took me long enough though.